there's the recording. So I think this may be everybody. So welcome back, everybody. Hello, hello. Not rhetorical, actually saying hi to everybody. Hello. It feels like it's been forever. It's only been a week. The twice a week class schedule is very different for me. I don't like being away for a whole week. It seems like it's too much time in between to not to touch base. So I'm happy to be back. Plus, there's the reality of the fact that stats classes over 3 hours. Nobody wants that. Not me, not you. It's just, yeah, there comes a point where your brain is full. So I think the 2 day a week schedule works best in that situation. But I'm glad to be back. We have formative assessment number 2, the next thing due, that's due on Monday, so we'll go over it next Tuesday. And homework 2 is available, and that is due in, 2 weeks? The 15th, I think that sounds right. You should be able to do all of it. It's some correlations and some chi-squares and stuff like that. Let me know if you run into any problems. Does anyone have questions on homework 2 yet? If you've taken a look at it? Not yet? That's fine. I'm just asking. I know it's way out there. Are you excited to start something new? Yes, that is a rhetorical question, but thank you for playing along. All right. So those of you who've had stats classes before, my guess is that everything we've talked about up to this point is somewhat familiar territory. I expect that this will also be familiar in terms of the content. However, the approach that I'm going to take in teaching it is going to be perhaps a little bit different than what you're used to. And the reason is that I am secretly preparing you to be able to take advanced coursework with me. So I'm teaching this from the perspective of what would I want you to know to be able to build on this later. I do this for that reason, but also because I think it's easier to learn something in a general way and then say, here's a specific case, here's a specific case, here's a specific case, than to learn separate things as if they're entirely separate. The latter is harder and it takes up more space. So that is to say, I have a slightly different way of talking about these things than what you may be used to, but I feel like it will help you in the long run. And even if you're here only in the short run, that's fine. I still think it's easier to talk about it this way. So that's the caveat to my strategy. All right, we get the thing started. And here we go. So welcome to general linear models. So we are leaving the world of univariate and bivariate and moving into the idea of prediction. So first up is going to be some new terminology, and then introducing this modeling framework from the lens of just a Pearson correlation. So the things that we're going to talk about in this lecture are equivalent to Pearson correlation, but it's expressing that using a different way of talking about it, expressing it from the perspective of one variable predicting another, and that perspective is what allows us to build on this to do things that Pearson's correlation can't, such as nonlinear relationships, such as dealing with nominal or ordinal variables beyond just quantitative and binary. So this is new terminology, new notation, and new words for a familiar idea. That's where we're headed. So away we go. First off, what have we done so far? Just a brief review. Univariate stats is where we started, and then learning about hypothesis testing from the perspective of testing a sample mean against a population mean. You can do that with the Z if you know what the variance is supposed to be, or you have enough people. You can do it with the T if you don't have enough people and you don't know what the variance is supposed to be. Then we did bivariate measures of association, and which one is appropriate depends on what kind of variable you're trying to associate. If you have 2 quantitative variables, that's what Pearson correlation is for. If you have one of the variables or both are ordinal, or you're concerned about extreme values in a quantitative variable, that's what Spearman's correlation is for, which is the same thing as Pearson, but conducted on rank-ordered data instead of the original numbers. And then if you have categorical predictors and you want to see, categorical variables, and you want to see if they're associated, that's what the world of Pearson's chi-square and contingency tables are associated with. So in all of these things, other than my slip of the tongue there just a second ago, we're just talking about variables, right? If two variables are associated or describing one variable at a time, now we're going to switch to a lens of having predictors and outcomes. So variables that play a particular role, not just how they're measured. So in terms of doing data analysis, we're starting into the process now of how would you go about using these techniques to answer questions in your research or in the real world. So quantitative data analysis broadly construed. Step 1 is to get the data. Step 2 is to enter it into software and verify its accuracy. And then step 3 would be what we've just done so far in this class. For each variable that you're going to be examining, you want to describe it univariately, so central tendency, dispersion, that kind of stuff, or how many people in each category, how many categories are represented if it's categorical, and those univariate and bivariate measures of association, univariate stats, bivariate measures of association, can tell you whether or not the data are accurate. So they can help you identify extreme values that are implausible or data entry errors or those kinds of things. So then we're moving into how would you actually go about answering most research questions is going to involve a model. Most research questions require a model of some kind. There's all kinds of models for all kinds of questions for all kinds of data. And this is an iterative process. There's never going to be a point at which you have one model and you're done. In reality, it's more like you estimate the model, you check the results, something comes to you, you try to do it a different way, you add in a new variable or you take out a variable that you decided didn't matter, and it's like after this iterative process is gone through, that's the point at which you would interpret things. So then the result that you end up reporting is a much neater, cleaner version of the messy process that you arrived at to get to that point. And by the way, in terms of writing, just a few pointers. The way that we talk colloquially, like I'm running an analysis or running a model, you don't write that in professional writing. You would say that you calculated or estimated. If it's a model, you would say estimate. If it's something that has a ready-made formula, you can say calculate, but estimate works for most causes. So we don't run, we estimate. So in terms of talking about the role of a given variable with respect to answering a research question about it, there's two main camps. And so on this slide 4, I have listed all of the synonyms that I'm aware of for each of these different roles. So on the left side here, so if you have a question about what is the role of a variable, let's call it x, in explaining or predicting another variable called y. The reason, so the thing that's supposed to be causing an effect or that is responsible for something, the explainer, that is going to be x in my notation always. The variable that it is explaining, the outcome, is going to be y. So the terms that I use most frequently to map onto these ideas is a predictor versus an outcome. A predictor is the explainer, the outcome is the result. Other terminology that you may see, an explainer variable in X is exogenous. That is a term that shows up in path analysis and structural equation models. The outcome that is explained, the Y variable, is endogenous. The mnemonic that I use for these, by the way, is that X goes with exogenous. Those are two words you're probably never going to hear me say again, though. It's just predictor or outcome because they work most generically for most situations. If you've taken a course on experimental design, does that sound familiar to anybody? Yeah, like within subjects, between subjects, and all that kind of stuff. These two ideas in that language, the X predictor variable is often called an independent variable, and that term in particular is usually referring to a predictor that is manipulated. So if you randomly assign people to either a control group or a treatment group, that is your independent variable or your IV. Then the corresponding term in terms of the outcome is DV, or dependent variable. That's the thing you're measuring to see if your IV had an effect. And so IV, DV are synonymous with predictor outcome, but they tend to be used in experimental designs rather than observational designs. The last set is covariate and criterion. So criterion is a term referring to an outcome variable that's often used in the context of multiple regression. We would say, what is the criterion that you are predicting? So the word itself means like a standard, like what are the criteria that you have to meet to do X, Y, and Z. That's not how it's being used in this context. Criterion is an outcome variable. I don't use that term very often, but it was what I grew up with when I was in regression coursework. Covariate has two different meanings. A covariate in an experimental study is a variable that is collected as a predictor that you did not manipulate. So if you wanted to see if treatment versus control matters after you control for age or after you control for some other previous background variable, then that maps onto the idea of what's known as ANCOVA, or analysis of covariance, where the C is for covariate. So covariate in that context means a predictor variable that you did not manipulate. That's usually a quantitative variable. But covariate also means a predictor that someone else cares about who's not you. So in the context of testing research hypotheses, there are always things that somebody wants you to control for. And if you don't control for it, someone's going to yell at you and insist that you put it in your model. There are special variables like that in every research context. So my first area of research was cognitive aging, I would say. That was what I did my dissertation on and my postdoctoral work. And in studying older adults and their changes in cognition, you absolutely have to control for chronological age. That is the first variable in the model. If you don't put it in there, someone's going to yell at you because age is boring. Age is not an explainer. You have to just control for it and then see what else matters. Is it health or previous experience or education or blah, 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 but age is the thing. In a lot of research looking at the effects of economic outcomes, controlling for socioeconomic status, so you got to put that in there or someone's going to yell at you. So can you think of examples of variables like that in your fields? Something that you have to control for as part of your analysis?
Yeah, disability.
Disability in predicting what?
Could be like problem behavior, level of problem behavior, cognitive ability. I don't know.
I don't know is exactly right. Like all the stuff, right? You have to control for whether someone is, say, neurotypically developing or on a different trajectory or has been diagnosed with whatever issue, problem, or giftedness. Like that's a thing. Anyone else want to play?
So on my second year paper, I was working on finding a relationship between video game playing and its effect on behavioral problems in adolescents. And one of the covariates that I used there was cognitive stimulation and emotional stimulation received at home.
Cognitive and emotional stimulation. Was that your idea or someone
That
else's
no,
idea?
I found it from a paper.
You found it from a paper. Okay. Every research field has variables like these. And so when you see predictors in a model, different X variables, some of them referred to as predictors and some of them referred to as covariates. That is a semantic distinction. A covariate means that someone else cared about it and so you have to care about it, or it's been shown to be related to what you're studying and so you have to demonstrate that the thing you're adding is above and beyond what people already know. So one person's covariate was a previous person's research career. Science is accumulative. So I just want you to be familiar with all the different words that people use to describe the same thing. So if a variable is an explainer, a predictor, covariate or not, all of those things, put that in one column in your head. Those are reasons, those are predictors that go into the model. The other side, the outcome. What is the thing that you're trying to say you have predicted, explained, or now understand better as a result of the analysis? Okay, with me so far? All right. So let's practice. So here's some example research questions. As somebody who does a lot of quantitative analysis and consultation with PIs from other areas, I have lots of experience seeing research questions that span between great and what? So here's a few examples. For each of these, I want us to try and identify which variables in the question are to be predictors and which are to be outcomes, as well as your best guess to what kind of variable each is based on how the question is worded. So whether it's quantitative, and if so, maybe what kind, or whether it's categorical, and if so, what kind. Okay, you want to play? Ready to play? All right. So first question, to what extent does positive feedback improve performance, speed, and accuracy more than neutral feedback? So what is X according to the way that question is worded? What is the predictor?
Types of feedback.
Yeah, and what's your best guess as to how feedback is measured? What kind of variable is it?
Maybe like quantitative, like a rating scale,
Could be.
or it could be categorical, and then we could just like use words like good, like.
So, yeah, so Doris Ann, what made you say feedback?
Because there's both positive and neutral feedback indicating that the researcher is going to manipulate which kind of feedback the participants receive.
That would be a good guess. That's probably what I would say too. And so, how positive or how neutral? It could be a quantitative variable as well if it were measured. So, if you were going into a classroom and watching what happened, right, you might have a rating scale, like Fayaz said, somewhere between neutral and all the way positive, and there might be gradations. So, it's not exactly clear, but it sounds sort of binary in the way that the question is worded. Now, what are the outcomes?
Performance, speed, and accuracy.
Yeah, so in that case, what do you think speed is going to look like as a variable?
How the time. So
Time.
it'd be quantitative.
Be quantitative. And is it going to have any boundaries?
Yes, because there is a bare minimum amount of time that they can't go any faster than that.
Yeah, some minimum threshold based on whatever they're doing. Above 0, and it's probably going to be skewed, I would guess too. Response times are often skewed. How about accuracy?
Number of answers getting correct on a specific test.
So that sounds quantitative. Do you think there's any boundaries on that?
Yes, definitely. It's going to be, it cannot be continuous, right? It has to be discrete. Yeah.
It would be, depending on whether you think of it as number correct or percentage
Percentage,
correct.
yeah.
If it's percentage, it won't be discrete, but it is bounded. So you can think of it as somewhere between 0 and 100%.
100.
So outcomes like that actually need a special model. That's in another class, but a lot of times people pretend that they're continuous enough to be treated in this sort of analysis. Do you think it would be useful to predict speed and accuracy in separate models or at the same time?
Separately.
Separately? Yeah, we would want to know, in order to answer the question, whether it affects speed and whether feedback affects accuracy. But can you think of any reason why we might want to put them together also?
Interaction. We need to see their interaction. It's like they might be affecting, confounding each other, speed and accuracy.
Yeah, speed accuracy trade-off is a thing. So you can see to what extent people are faster because they are less accurate, right? So there's a potential correlation between them. I wouldn't necessarily say interaction because that word has a very specific meaning, but certainly they're going to be associated. An interaction term, by the way, is a multiplication of the two, whereas this would be more of just an association. So if I wanted to predict both simultaneously to look at their association, I would need what's called a multivariate model to do that, where multi means multiple outcomes. The models we're going to work with this semester are univariate, but once you can do a univariate model, then you can extend that knowledge into predicting more than one outcome at the same time. So good. Is faster academic growth in elementary school related to more frequent reading to children when they are in preschool? What is my predictor and what is my outcome?
Frequent reading while in preschool would be a predictor. With academic Growth being an outcome?
Ah. Frequent reading as a predictor, and based on that wording, I have no idea how it's measured. Could be anything. Could be a Likert scale, it could be a count of times, it could be anything. But academic growth. So that phrasing right there is actually pointing to another predictor as well as an outcome. What is the other predictor I would need in order to examine growth? Doris Ann, if you're talking, I can't hear you.
Yeah, I'm just trying to guess and see what other people say. I was just gonna say you would need to know their baseline or where they're starting to be able to measure growth, or whatever the norm is for preschoolers.
Yeah, you'd have to know their baseline, which means you'd have to see what happens as they get older, right? Growth in elementary school means that you're measuring them multiple times. So you'd have to be able to measure somebody at least twice to know relative to their baseline how much they grew. So this question implies a predictor that's not only frequency of reading, but also time. Time as a predictor is how growth is indexed, and the interaction of the two would tell you if change over time is related to how much reading you had in preschool. But this is an example of a badly worded question because it's like academic growth. Growth of what? Grades? Reading? Like academic what? So I don't know what the outcome is in this question. Academic something. I just know that time is involved because of the word growth. That's the next class. Longitudinal models at 2 o'clock. Last but not least, how effective is teacher training for creating higher rates of positive feedback to a teacher's students? What's the predictor? What's the outcome?
The training provided to the teachers, like pre-service teachers, that's going to be the predictor. And outcome is going to be the positive feedback these teachers receive once they started teaching.
Yeah, so the outcome in this case is positive feedback. The way that I had intended it was how much the teacher is providing positive feedback. So like teachers who have more training might give more feedback. That was sort of the idea that I mentioned. By the way, what does pre-service mean exactly?
It's like they're hoping to be teachers pretty soon.
Okay.
That's how I make of it. So they're like, these are the folks who are enrolled into our teachers education program. And so we call them pre-service teachers.
Okay.
Oh.
I've heard that word so many times, and I've always wanted to ask what it meant, and I never got the chance. So like students who are training to be teachers then. Okay.
Yes. My interpretation of that is the people we need to tell to run far away from being a teacher, but we really do. So.
Not that we're being cynical. Well, I like teaching. That's actually why I took the gig, so to speak. I thought I was going to grow up to be a stats consultant, and I was all set to have that as a career path, and it was my first experience teaching actually as a postdoc that changed my mind. I thought, well, I can go into academia and fake a research program long enough for them to let me teach. I can do that. And don't tell them, but that's what I did. So teaching isn't all bad. Even if I'm post-service. Was that what you call it? Like after you're in the gig? Or are you just service then? Do we know?
I guess you're like a full service teacher.
A full service teacher. There you go. From what I understand, teachers are not only full service, but like extended warranty. Like they're working on nights and weekends doing things for their students. So, anywho, so teacher training is the predictor in this case. The extent to which a teacher provides feedback to each of his or her students is the outcome. Now, in this case, I also want to point out levels of analysis. Who is the outcome being measured for? The teacher? No, the kids. And then who is the predictor being measured for? Yeah, the teacher is the predictor. So this is an example of when the models we're going to learn in this class would also be insufficient, because you have to be able to build something into the model that connects each teacher to the students the outcome is pertains to. So that type of data setup, when you have multiple students nested within multiple teachers or classrooms, is what's known as clustered data. And that is a class coming this fall that I teach. So you can come and learn about how to do these sorts of analyses in that situation as well. If you have survey respondents from multiple countries, or you have employees from multiple businesses, there's a lot of instances in which you see the outcome being measured at one level, but a predictor being measured at a higher level. And so you can use models in that situation, but they have to be more complicated as a result. So just a little bit of putting a plug in for the other things that I can teach you. In this class, however, there are two ways to think about a relationship between an X predictor and a Y outcome. And you can think of it in terms of causal inference, or you can think of it in terms of associative inference. We are always going to do the latter. So to be able to say, for instance, that your predictor causes an outcome, like capital C causes is a very particular word, you have to be able to say that the predictor came first, what's known as temporal precedence. You have to be able to say that the predictor was under complete control of the experiment, so it's a manipulated variable. And your design has to eliminate any other confounds or alternative explanations. So all that stuff has to be in place before you can say the word cause, regardless of what your model looks like, regardless of what kind of predictors you have. So I'm going to go ahead and assume that most of the research that you would be dealing with is not that kind. So instead, we can say things like X relates to Y. I think it's okay to say predict. You just can't say cause. Cause is a special reserved word that someone will yell at you if you use it incorrectly. So you can say that these things are related to each other, and we would call that associative or correlational design. And because we don't have experimental control on our side, the way that we can still try to rule out alternative explanations rather than to use experimental control is to use statistical control. The idea of also putting into the model competing explanations for why something might happen and seeing to what extent the thing you care about still matters. So as an example, it turns out that if you are pregnant and you smoke a lot, that your child may have more issues than people who are pregnant and they didn't smoke a lot. So that's a well-known phenomenon that's been studied, and the question is always why. Is it the nicotine, or is it other things that correspond with the decision to either start or keep smoking while someone is pregnant? So in that literature, they want to try and pull apart the effects of socioeconomic status or education level from the use of nicotine and the amount of nicotine. And so then education level and all these things become competing explanations for the phenomenon that would go into the model to see to what extent, say, the nicotine per se still matters after you control for these other things. So that's the kind of language that we can use to sort of get at the same ideas as, okay, what really matters and what is just extra in situations in which you can't do that in experimental design. But because it's not truly controlled for, you have to be careful with the language. So I'm going to say things like X predicts Y, X relates to Y, but I will never say cause. And by the way, this phrase correlational, that doesn't just refer to correlations. It's any kind of association, whether it's specified as a correlation or as a chi-square or as some other way of talking about it. All right, so how are we doing so far? Good? All right, so new words, predictors and outcomes, and which is which depends entirely on the way the question is phrased. So moving on then to predictive linear models. If you have questions about more than two variables at a time, those questions are best answered using some kind of model. That means that the variables that are part of your question have to be identified as either predictors or outcomes. And the models that exist for predicting different outcomes have different names and they have different ways of predicting it based on the type of outcome. So what we are focusing on this semester, what is covered under the general linear model, is prediction of continue-ish outcomes. So quantitative outcomes that are supposed to be continuous and unbounded, or something that's reasonably plausible to it. That is what the general linear model is for. It turns out that the outcome itself doesn't have to have a normal distribution. That's a common misconception. But the amount of information that is left over after the model has had its prediction, that is supposed to have a normal distribution. So talking about the outcome marginally versus the residuals conditionally. We'll talk about that. But that's this semester. Literally any other kind of outcome is something else. So that is what you may hear a phrase from me and others, the term generalized linear models. Ized means not normal. So for outcomes that have boundaries, for outcomes that are not quantitative, for outcomes that are quantitative but skewed, I just have a list here of all the possibilities. And so if you were interested in learning more about those combinations, those are the words you can ask the Google about. In terms of a coursework strategy, I feel like the next class after this one is best served as the generalized linear modeling class that I'm offering a year from now. So if you want to learn how to predict outcomes that are not just continuous quantitative variables, come back to that class. That class also tackles multivariate analyses of each of these different kinds of variables. And so that's sort of like the next layer in terms of building blocks of learning how to do this kind of stuff. So this is just to set up the idea that even though all we're going to get to this semester is models for predicting outcomes that are quantitative, every other outcome under the sun has a model that goes with it. So don't fear if you never have an outcome that is continuous, because most people actually don't. They're pretty rare. So what does linear mean? So breaking apart each of the terms in general linear models, the term general actually has a very specific meaning. It means the outcome is quantitative and plausibly normal. The linear part refers to how the model creates a prediction, and it does so as a linear combination of variables in this form. So it's always constant times variable plus constant times variable. That is what linear means. It does not mean that the model can only specify linear relationships. We can still use this type of linear form to be able to specify nonlinear relationships. For example, if I had a predictor times a constant, that creates a slope, either positive or negative. If I add in another term that is the predictor squared, that creates a U-shape. Either this one, or I can't do my elbows, but this one, right? The idea of a quadratic term creates a nonlinear trend. So it still does so in a linear model, even though the resulting prediction is a nonlinear function. So it's linear in the parameters is the way they talk about this, as opposed to linear in the variables. So everything that we're going to do and most of what you will see has this kind of form to it as a linear model. Fortunately, this also means that we can include categorical predictors. So any kind of variable can be a predictor in a general linear model. They have special names depending on what kind of predictor it is, though. So this is where I get to the idea that I teach this differently than what you may have seen before. Each of these special cases is a general linear model. So historically, if you're trying to predict a quantitative outcome and you do so using quantitative predictor variables, that is called regression. It is simple regression if there's only one predictor, or multiple regression if there's more than one. Sometimes they throw the word linear in there too, although that's sort of redundant. It sometimes distinguishes a regression predicting a quantitative outcome versus a regression predicting a non-quantitative outcome, non-linear. If you have categorical predictors instead, so you have a quantitative outcome and the variables that you want to be predictors are binary, ordinal, or nominal, that's known as analysis of variance, or ANOVA is the way you pronounce that acronym. If you have both kinds, If you have a model that has predictors that are categorical and predictors that are quantitative, that is sometimes called multiple regression or analysis of covariance, where co means there's a covariate in addition to the categorical predictors. There are no other systems of models that I'm familiar with in statistics that make different names for different kinds of predictors. This is just a weird historical thing that developed because of differences in how these approaches were developed and, I would say, programmed in terms of how you could actually get the answers out before there were computers. What I believe is that it is easier to think of all of these things as one thing. The general linear model is how you predict a quantitative outcome that's supposed to be plausibly normal in terms of its residuals. You can do so with any kind of predictor you want. And so then you don't have to worry about which of these special cases you're in, and you can combine across them to do whatever it takes to answer your question. So this is the approach that I take in teaching this material. That also means that for the rest of the semester, you only have to learn one more thing in terms of software. In SAS, it's GLM. I might ask you to use a reg as another procedure for one or two questions, but most of what we'll do will be in SAS proc GLM. And in Stata, it's the option regress. Does everything. Okay, so is this sounding familiar to some of you who've had coursework in this before? I would also throw in one more correspondence. If you have a quantitative outcome and you have a single binary categorical predictor, do you know what that is called? If you've taken a stats class before, I can almost guarantee you've seen this, but it probably wasn't talked about that way. I'll phrase the question differently. So categorical outcome predicted by a binary predictor. What if I have two groups and I want to know if their means are different? If I say it that way, what do I do? No takers? No one wants to be wrong. You can also type anonymously in the chat window. You can send me DMs with your guesses, and then you don't have to look foolish if you're not right. That's actually my favorite part about Zoom teaching, is that one feature. Looking foolish. Yeah, you can look foolish in front of everyone in the chat window. It's totally up to you. But no one looks foolish to me. I just think that some students are more comfortable not typing to everyone. But you don't have a guess. No one's going to guess? Hypothesis tests. All of these are hypothesis tests. So that's a more general term. It's known as an independent or between groups t-test. If you have a quantitative outcome predicted by a binary variable, that is an independent groups t-test. So that's one more special case of what is actually just one thing. All right, so in terms of the outcomes, if you're predicting only one outcome, that is known as a univariate model. If you're predicting more than one outcome, that is a multivariate model. Come back to the generalized course to get the latter. In GLMs, the starting point of predicting an outcome is just to describe what's in the outcome to begin with. So we start from a univariate perspective. Okay, let's describe the outcome. Let's describe its central tendency. Let's describe its dispersion. So our very first model is this right here. These three little things. Welcome to your very first model. This is a general linear model that, hang on here, I lost the participant window. 1 second. No, I lost my chat window now. There we go. Okay, I'm back. So this model right here is known as an empty model because it has no predictors in it. So this is something that doesn't often get taught, but to me it has a very foundational role in helping you understand how this shit works. So here's some new notation for you. Y sub I. So that's the same. So when I say y sub I mean this thing. that refers to the column that holds the outcome variable. So y for each individual. So it has a subscript to denote that it's a variable. That is a function of a new term right here, which is beta 0. So I don't say beta sub 0 for whatever reason, it's just beta 0. You may also hear this called beta naught, but no, oh my God, no, it's beta 0. This thing is going to be a fixed effect, and more generally, a specific kind of fixed effect known as an intercept. The key feature of it is the lack of an I. Beta 0 is a constant, not a variable. It is one number to be found by the program that applies to everyone's score equally in creating a predicted outcome. E then is whatever beta 0 is not. So we'll get to that on the next page here. So in this case here, here's my model. If I don't know anything else about a person, my best guess for what their outcome's going to be is the grand mean, the sample's mean. That's the middle value. That should be the most likely value. So if I look at this picture down here, these are normal distributions stolen from Wikipedia, where the blue line, the red line, and the, I'm going to go with goldenrod. What did we decide this was before? Some of you had better names than that. Goldenrod is the crayon
Saffron.
name for this.
Saffron.
Saffron. Yes, I like that one. So blue, red, and saffron here. These are distributions that all have a mean of 0. So 0 is the most likely value within this distribution. So if I don't know anything else and I have a distribution for a variable that looks like this blue one, my best guess for any one person's score should be 0, because that's the middle. My best guess for any one person's score from the green one should be -2, because that's what its mean is. So beta 0 is the mean. That is the starting point for a prediction. Like, well, I don't know what they should get, just give them the mean. If you don't know anything else, that's the best guess. But then this other thing here, E, this is what's known as a residual. It is also known as error, that's why it's E. The role of that is foreshadowed by the differences between these. So what makes the blue line different from the red line, different from the saffron line? What distinguishes those?
The variation.
Yeah, the variation around the mean, right? The blue line is a lot taller because there's a lot less variance around the mean. The mean is a better guess, relatively speaking, for any one person from blue than a person from saffron. So that's E's job, is to index that part of the story. So E sub I, because each person gets their own, E is a variable, is known as a residual. It always has the same definition. A residual is the difference between what the model says the outcome should be and what it actually is. So Y sub I minus the prediction, that's what E is. So if you are somebody whose outcome Y is actually above the mean, your E will be positive. If you are somebody whose outcome is below the mean, your E will be negative. So the question then is, well, what does the model predict? This model predicts the same score for everybody. So E is another way of just saying the difference between each person's outcome and the person mean. And if you're thinking that sounds like variance, it's because it is. You've seen this before. So in this case, we're renaming what we used to call the sample variance as the variance of E specifically. And this term right here, this is sigma squared sub E. That's what I would call that. That is all of the variance that there is to be had in this Y outcome. This is our starting point. Okay, so my best guess for each person is the mean. How wrong is that? Right? That's what this residual variance, the sigma squared sub e, is telling me. How wrong is that? It's conveying all the deviations from that mean squared so that the positives and negatives don't cancel out. So you can think of this value of the variance of this variable that's given to us by the model as the worst you could possibly do. From here, our goal is to put predictor variables into the model to try and get a better predicted outcome for each person that should make the residual for each person smaller. And so what we want to know then is how much smaller, how much of the total variation in this outcome is reduced or explained by the model predictors. But in order to know how much it's reduced by, you got to know how much there was in the first place, the baseline, as said earlier. And if you're curious about why it's sigma squared now instead of s squared, the answer is because when people use model notation, it's always the population version. So this idea of y bar versus mu and s versus sigma, that's gone. It's going to be Greek letters from here on out. So we have beta as the fixed effect, and I use red and blue, by the way, to help us separate out what each component is doing. Betas are fixed effects, e's are residuals. We care about the variance across people in the residuals. We're going to use that as an indicator of model quality. So this is the baseline empty model, the worst we could do. It tells us, okay, what's the mean of the outcome? How much variance is there? Okay, now let's go. All right, questions? With me so far?
I just was hoping you could repeat something really quick, just what you
Sure.
said about explaining how variance or how much variance is explained by the model. Can you just repeat that part again?
Mm-hmm. So eventually what we want to know is of the total variation in the outcome, of all the reasons why people differ from each other, how much of that have we explained? 10%? 20%? In order to know that, we have to know how much variation was there in the first place, right? We need a baseline for how much it went down. So this model, the purpose of it is to give that baseline. This term right here, sigma squared e, that's residual variance. That's what it's going to be called. The variance of the e residuals, residual variance. In the empty model, it represents all the variance in the variable that there was in the first place, our baseline. Everything that we do from this point forward, we do with the goal of reducing that number, taking sigma squared e and making it smaller. Fewer reasons why people still differ from each other after we put our explainer reasons in as predictor variables. Okay, does that help? Okay, more words than you asked for, but they came to me, so I had to let them out. All right. So beyond empty models then, okay, how do we go about this process of testing hypotheses, answering research questions about what predictors matter in trying to capture outcome differences between people? Well, here's an example. Let's say that we have a quantitative predictor. Let's start there. So what I'm going to show you here is known as simple linear regression. By the way, don't ever call something simple. It's just offensive to whoever you're talking to. I hate papers that say things like obviously or clearly or things like that that imply that if you haven't followed it, it's your fault. So simple is not meant to be insulting, it just is, but it's meant to describe the situation in which you have a regression model with one predictor. And by using the word regression, they are implying that it is a quantitative predictor. That's where the terminology comes from. So what I'm going to show you under this umbrella here is literally Pearson's correlation with a new dress on. It's the same thing. It's a different way of approaching the problem that allows us to build. Because Pearson's correlation is limited. It only allows linear relationships and only for a pair of variables at a time. So in order to be able to expand the model in those future ways, we first have to get our handle on what it's like to do the thing we already know how to do using this new notation and a way of talking about it. So this is equivalent to a Pearson correlation, what I'm going to show you. So if I have this model here now, I've expanded it with this new term beta 1. So the betas are fixed effects. Note that there's not an I on either of them. They are constants, one number that applies equally to everyone. Come on, there we go. Beta 1 is a slope. It is always the same definition to how to explain a slope. It is the difference in the outcome for a 1 unit difference in the predictor. If this sounds a lot like 8th grade algebra to you, yes. It used to be y equals mx plus b in my algebra class. And they put b as the constant, as it was called at the end. We rearranged it and we're relabeling it, but it's the same exact idea. This is an equation for a line. So we have a new variable included as a predictor, and I'm using x specifically for predictors. Note that x has an I subscript because each person has one. So each person has a y, each person has an x, and therefore, because each person has a y, each person has an e. So e is a variable, x is a variable, y is a variable. Beta 0 and beta 1 don't have i's because they're constants. So beta 1 is a slope. People say change in y for a 1 unit change in x. You can say that. I try to say difference in y for a 1 unit difference in x because I'm sensitive to the idea of longitudinal versus cross-sectional, and people are not changing into each other, they're differing from each other, but that may be a semantic distinction that only I care about. Rise over run was another one. Do you remember that? I'm picturing like a triangle, like a hypotenuse sort of thing. Any others you can think of for slope definitions, phrases? Or if you don't have words coming to you, you can just do this, right? Different slopes for different folks. So the slope is an unstandardized way of expressing how x relates to y. And I say unstandardized because it's in the units of the original variables. So it's the difference in y, in whatever units y is, for a 1 unit difference in x. So in order to know what to do with the slope, we got to know what the units are. Is it dollars per year? Is it inches per pound? Is it the units of GPA for units of income of your parents? Like you got to know the units to know what to do with these numbers. But fortunately, we can get there just by knowing what the Pearson correlation is. So correlation between the variables is standardized. It stripped away the units. So if we put the units back on, we get our slope. So in the case of having one predictor variable in a model, there's a handy-dandy formula. The correlation times the standard deviation of the y outcome divided by the standard deviation of the x predictor. That's how you get your slope. So it's in units of y per units of x. And so in this case, if we had z-scored variables, so if they were standardized to each have a standard deviation of 1, then the slope would be the same thing as the correlation. If the variables are not standardized, the two will be different, but they tell you the same thing. The intercept then is always defined the same way also. An intercept in this class and in every other class I teach is the same thing, which is very comforting. It is the expected outcome when predictor is 0, when all the predictors in the model are 0, but right now there's only 1. So the role of this fixed intercept beta 0 is to adjust for any mean difference between x and y. That's what it's for. If there is no mean difference, the intercept is going to be 0. So this all works even if we mess with the units. So what if instead of having each variable have a standard deviation of 1, which is what it is right here, What if X now has what is known as a T distribution, I think sometimes it's called that, a T-score, of a mean of 50, standard deviation of 10, but we keep Y the same? Well, then that same Pearson correlation, when you put the units back on it, translates into a fixed slope of 0.05. So a 1 unit change in X, which is not a very big change anymore, considering the new scale, results in a 0.05 change in Y. And because of the differences in the mean, the fixed intercept would be 2.5. So if X is 0, Y is 2.5. From there, for every unit higher X, Y goes up by 0.05. It's the same relationship, just changing the units. If we go the other way, now if all of a sudden Y has a much broader scale, where the mean is 50 and the standard deviation is 10, but X is standardized. Same thing, beta 1 is the change in Y for a 1 unit change in X. A 1 unit change in X now is a full standard deviation, which has to result in a bigger change in Y because Y is a lot more spread out. So now the slope is 5. Because they still differ in their means, the intercept has to pick that up. And so if X is 0, then the intercept is 50. So if X is in the middle, Y is going to be 50. From there, for every unit change in X, Y goes up by 5. So this is all just to say that units matter. And you have to know what the units are of your X and of your Y in order to know what to make of these fixed effects. They are unstandardized coefficients. All right, with me so far? Or still, I should say. It's too far into the class to say so far. We've crossed over into still. I think still starts around 113, as far as I can tell. So, here's a question then. Beta 0 is kind of like the anchor point of the model. Here's why beta 0 should be meaningful. This is a map of a very busy airport. Does anyone recognize where this terminal B is from? EIC? I don't know that abbreviation.
It's the one that's here in Cedar Rapids.
Oh. Yeah, no, Cedar Rapids has like one check stand and like one vending machine, right? This is not Terminal B at Cedar Rapids. Much bigger than that. Think of other big airports. I believe this is the busiest airport in the world, or the United States at least. That helps you.
The one in Atlanta.
Atlanta. Are you getting the ATL, Mackenzie? Is that what you're doing here? Yes, I appreciate the sign language. Yes, this is the ATL. And back when I was in a commuter relationship with my now husband when he worked at the University of Georgia, I got to know the ATL very well. And so when I arrive at Terminal B, I have 45 minutes to make my connection, which is fine in Atlanta. It's very well organized. I need to get some lunch. My go-to when I'm in an airport is always Chinese food. So I got the Manchu Wok or the Panda or whatever, because I know what to expect. It's fast. I can get my stuff and get moving. What do I need to know to figure out how to get to the Chinese food in Terminal B?
The location of the Chinese food.
I gotta know that, but what do I gotta know first to know how to get there?
Where you are.
Where you are, yes. That is step 1 in reading these maps, is to find the "you are here" star, right? Because everything is relative to that. I need to know if I need to go left or right when I get up the escalator or off the elevator. So the "you are here" star is essential to being able to read the map. So in thinking about the idea of an intercept as the "you are here" star of your model, we want to make sure that it's in a good central place to talk about it. So here's an example of when this doesn't work in terms of units. Let's say that I am going to be looking at the prediction of annual income in thousands of dollars from years of education. So this is the same data we've been playing with. We looked at Pearson correlations. I know that there is a Pearson correlation between these two variables. So let's say that I put those two variables directly in the model. I put in years of education as my predictor, and I put in income in thousands of dollars as my outcome. And I put this into SAS or Stata, and here are the numbers that come out. So this little term right here, I think I forgot to explain this. That y sub I with a caret thing on top, that's known as y hat. Y hat is the total predicted outcome from all the model predictors. So it's an abbreviation for what the model is. So y hat here for any individual says that anybody with the same level of education has the same expected income based on this linear function. That's why E is gone. So this is the predicted part. E then takes over to say what is left. So in this, here is the line that is predicted by the model. And if we try to interpret the coefficients, you'll see that there is maybe a problem. So 1.82, that is the fixed effect, as it is called, a fixed slope for education. If I were to put that 1.82 into a sentence, does anyone want to try? No, Alex says no, that's fine. It's too soon, that's fine. Does anyone else want to try? To put the 1.82 into a sentence?
We say like 1.82 times, something like that.
Start off with, for every, I'll remind you of what a slope is, the definition, and then you can put it into the story. A slope is the change in y for a 1 unit change in x.
For every change in the xi, there is going to be a 1.82 times change in the outcome.
Close, not times, because it's not multiplying. It's 1.82 higher per unit of x. So x is in years of education. So for every additional year of education, y, which is your money, is expected to be higher by 1.82. So that is $1,820. It's in $1,000 units. So it pays off to go to school, literally. Now, what is an expected value, though, in terms of the intercept here? Yeah, Houston, we have a problem. My expected income is negative $7,000. So I'm expected to be in debt. Is that how that works? But who is that the expected income level for? What kind of person is expected to make negative $7.89 thousand a year?
No education?
No education. Not a new graduate, like literally no school. I know I keep saying literally a lot. That's because my 5-year-old has adopted this word, and it's in every one of his sentences now. Now I've got the habit. Literally, mommy? Yeah. So literally no education. Now, what are the odds that someone like that was in my survey who had never even been to first grade? Probably not. There could be people with no education. Odds are good they are not responding to a research survey. This is the general social survey. So I've drawn an extension to the regression line. This is a plot that I made in SAS, by the way, to show where the intercept is actually predicting. Yeah, negative money. Yeah, just hang on, it'll get better. Eventually you will get out of debt. I know what that feels like. I was there once, but you just gotta hang in there. But yeah, the reason the intercept is so crazy is because it's a "you are here" sign that's like outside the airport. It's a reference point for the model that's too far away from the data. So to make sure that we have an intercept that's interpretable as a reference point for what the effect of the predictors then do, we fix it. So for every predictor that is going to go into any model in any of my classes, this is universal, I want to make sure that 0 is a meaningful value if it's not already. So to maintain that interpretation of the intercept, I'm going to do something that's called centering of my predictor. It is a linear transformation. It is subtracting a constant so that 0 is now meaningful. So for instance, I'm going to make a new variable. So I'm going to take the column in my data set that was called education, and I'm going to subtract 12 from it and make a new column with the result. And if I put in that new variable instead, lo and behold, the slope is exactly the same because it's still the same relationship. A linear transformation adapts all of the values equally. It's not distorting anything. It's just changing where the center is. But what it's done is fix my intercept. So now my beta 0 fixed intercept was estimated at 14 because it's a different reference point for the model. It is the predicted income level for somebody with a high school education in the sample. So that's my new middle "you are here" sign, and I can talk about the effect of education as for every additional year, your income is predicted to go up by 1.82. For every year less, so if you go from say 12th grade to 11th grade, your income is predicted to go down. So a positive slope has the same interpretation as a positive correlation. If x goes up, y goes up is positive. If x goes up, y goes down is negative. It's just that the numbers here refer to the particular units that the variables are measured in, years and $1,000 in this example. So why 12? Because 12 is meaningful. At least within the United States, 12 years of education corresponds to a high school degree. But the good news is that there's really no wrong way to center, only weird. Meaning that you can choose any reference point for your intercept that you want in these models, and it doesn't really matter. It's all about interpretation and making sure that each of your parameters has meaning in the context of the analysis. In other more advanced models, you can break things by trying to have a predictor whose 0 value is too far away from the data, but that won't happen here. So I say there's no wrong way, it's only weird. My penchant, because I know what's coming after this, is to start by saying always make sure that your predictor has a meaningful 0 value. If it already does, you can leave it alone. Like if you have a predictor that's like number of times you've been in prison, 0 could happen. Right? 0 would be the goal. So you could leave that one alone. But for something like years of education, 0 isn't going to happen. All right. Still with me? Ish. So big picture, what we're doing here, I'm showing you a way to talk about how variables are related that allows us to build on what we can say with just 2 at a time. We're starting with just 2 at a time to describe what you know is a Pearson correlation with this new language and new notation that allows us to build on that. So this is a regression model that describes how y is predicted by an x linearly. So for every unit more x, the same change in y happens, so it's a constant change. Everywhere along the line, you have the same increment of 1.82 for each instance. But this framework allows us to put in other predictors at the same time. It allows us to look at non-linear effects of these predictors, and it allows us to expand to not just quantitative predictors, but also to categorical predictors of all kinds. So it's a jumping off point for more fun stuff to come. And then E is going to be what's left. So do you see how this line is sort of stabbing through the data, but it's not perfect, right? Like look at this person up here. They're making like $70,000 a year with only a bachelor's degree. What's that about? And if I zero in just on this column here, look at all the differences between people with a bachelor's degree, starting from almost nothing up to $70,000. That's E. That's what's left. So E then, the idea is how far off your outcome is from the one that's predicted. All of these people in this row right here have the same level of education. So it has to be something else that's differentiating their outcomes. So that would be what the model has left to accomplish, is the variability around this regression line. And that's what's captured by each individual person's E. And that variability across the E's is how we're going to indicate how well the model does in terms of predicting an outcome in an absolute sense. By how much did the E's become smaller relative to a model without the predictor in it? That is going to be known as what is the model R-square value, for those of you who've seen this stuff before. All right. So that, then, this last piece here, E is always defined the same way. It is the difference between what you actually got for your outcome and what the model said you should get. What the model said you should get is y hat. So if I have my y hat right here that tells me what the predicted outcome is as a function of x, I can substitute in that thing right here and then solve for E. So E is defined as your real outcome minus the one predicted by the model given by y hat. So in theory, if x matters, each person's E should be smaller than what it was before adding x. So then we have the same formula that we had before in terms of how we establish the variance of the E's, but now how we have defined E has changed. In this formula, E is the difference between the regression line and what each outcome actually was. So we should hope that the new sigma squared E from this model, adding in education, for example, is smaller than the residual variance from the empty model, which was all the variance there was to begin with. And we end up with an n-2 here in the variance formula because we spent 2 degrees of freedom to do this. In order to find the E for each person, we had to know the beta 0 and the beta 1 as estimated from the data. So that's why it's n-2. Can you guess what this denominator would be if I added a second predictor? Not a trick question. If I've got 2 betas here and it's n-2, what if I add another beta? n-3. What if I add another one? n-4. Yeah. So this is the idea of denominator degrees of freedom. How many more betas could you possibly add in explaining this outcome? That's what it's telling you, and it's a function of your sample size. All right. So questions before we adjourn for the day. Yeah, n-n, you're out. At that point, you've explained everything.
I have a question, Lisa.
Sure.
So are GLM and OLS the same thing?
OLS is a way of estimating GLMs. It stands for ordinary least squares, and it works out that the values that these numbers take on through ordinary least squares regression are the ones that collectively make the E variance the smallest. They minimize the sum of squared error. So yes, but GLMs can also be estimated other ways. Maximizing a likelihood as opposed to minimizing error is sometimes the same and sometimes not the same. So OLS is a method of estimating GLMs.
The paper that I'm using as a model uses that term, so that's why I was confused.
Yeah, it's ordinary least squares, and there's other kinds of least squares that are not ordinary also. So, extraordinary, like you guys. All right, it is Thursday, which means I say have a good weekend. Let me know if you need anything, and please do your formative assessment before class next time. All right? All right. Peace out, everybody. Enjoy yourselves.